Okay, so what we do is we have some type of physical system that we want to learn about, and so we do measurements that we put into a model, and then with this model we can then play and see how, according to this model, the system should work, and then we can couple this back into our physical system, see if that kind of corresponds, and we can do more measurements if we're not satisfied with this model. So why do people like modeling? This mathematical modeling becomes extremely popular everywhere, and rightly so, because it allows you to make some type of mental picture of what is going on offline, try out what this would mean for the system, and see if that works. And if that works, it kind of means that the person who is developing the model says, okay, I have some understanding of what's going on. So it's like trying to get a grasp, an understanding of what this physical model is about. So it can be quite helpful. At the same time, doing experiments and measurements is also still, in most cases, absolutely necessary. So it's these two which go hand in hand, and so typical research projects will have an experimental side and a modeling side, and they're trying to come up with a good marriage so that the insight in the system is improved, and so that you can then use this insight to innovate, basically, come up with new ways of doing things. Okay, so that's something that engineers and scientists do very often. So if you have a system, you may have some inputs typically, and some outputs, and then you control the system. There's some control variables, but there's also noise variables, things which you don't actually control. And so both control variables and noise variables have impact on what the actual output is. It's also for your experiment you will have control variables, which we call the factors, which you have to have at least 4. But there will be other things going on as well. So there will be noise variables, which you know about or don't know about. And that's the reason why you want to randomize your experiments, because these noise variables may have some tendency during your experimentation. Okay. So if you have a system which, for instance, you have an electrical system and you measure current and voltage, you get something that looks like Ohm's law. If you look at it in more detail, you will see some deviation of the model, or some type of error. And so this variation, this variability on the value is something, of course, which is of interest to us. Because if we can quantify this variation, why it's interesting to know about this variation, if we can quantify that variation, we can then, based on this variation, when we're comparing different situations, make statistical statements about the significance of the difference that we see. Okay, and so that's why this variation becomes quite important. So for our decision making, it becomes important to see if we're making a decision to go to this, stay with the old situation or go to the new situation. So we want to be able to do that, and we do that based on the averages, but also on the variability, the variance around this average. And we'll come back to this later. But it's something that comes back throughout the course. So we'll get to know this quite well. We make a distinction between discrete random variables and continuous random variables. So examples are given here for continuous. Discrete, you have things like defects or persons, or so there's these two types of variables, we asked for your project to have at least two continuous variables. Okay.